What I want to do today is look at two more number systems, and then I want to look at a couple binary codes. So we already talked about base 2 numbers, binary. Of course, we already know about base 10 because we use base 10. But there are two other number systems that are common with digital devices. One is base 8, that's called octal, and the other is base 16, hexadecimal. So I want to look at those. But this table here compares the number systems that we use when we study PLCs. We use all the number systems, base 10, base 8, hex, base 2, and I just kind of have this so you can kind of compare the number systems. Notice that, well, this hexadecimal looks kind of weird because it starts at 0. All the number systems start counting at 0, but in hex I go 0 through 9, and I start using letters of the alphabet. So we'll see how that works today. And then base 8, look at base 8. I go 0 to 7, and then we start counting. It looks like a 10 and 1 0, 1 1, a 10, 11, 12. So we don't go beyond 8. So we'll look at how that works. So let's get into the first PowerPoint, and this will talk about octal numbers, hexadecimal numbers. All right, so the first thing to remember is that no matter what kind of number system we're using, if we're using a base 10, if we're using base 2, if we're using base 8, if we're using base 16, no matter what kind of number system we're using, the digital device only understands binary. So if I'm in base 10, if I'm in base 8, if I'm in base 16, and I send any information in those number systems into a digital device, that number system has to be converted to binary. Machine language is binary. Computers only understand zeros and ones. So any other number system like base 10 or hex and octal, that's just for humans. It's just for convenience of writing or looking at things that are already digitized. So all the other systems are for us. Base 2 is for the digital device. That's the takeaway. So it's convenient sometimes to write quantities and other number systems because, of course, in binary, you have a lot of digits you have to use to represent anything. You want to represent a number, you want to represent a piece of data. It takes a lot of zeros and ones, so sometimes it's convenient to represent those zeros and ones in other number systems to make the number look a little smaller. So the first one I want to talk about is base 8. Base 8 is called octal. Now, this is kind of a natural fit for the PLC or for digital device, because you might remember when we talked about sizing words and bits and bytes, we said that if I have 8 bits, that's a byte. And typically in digital devices, when you want to code something or encode something, you can do it with bytes or something bigger than the byte. So say, for example, your desktop, your computer, or even your cell phone. If you save some information, a picture, a word, or if you maybe you type out something in a text message, each character is entered into the microprocessor in groups of 8 in bytes. In most digital devices, the smallest piece of information you can access is a byte. Not true with PLCs, as I said, I think a couple lectures ago. PLCs, you can actually address a bit. PLCs are bit-oriented. Most other digital devices are byte-oriented. But since a byte is kind of a natural digital size, 1 byte is 8 bits, then this octal number system, base 8, is kind of a natural fit. So go back to what we said about number systems in general. The base tells us the number of symbols in the number system. And if I take the base minus 1, it tells us the value of the highest symbol in any number system. So base 8 would have 8 symbols, and if I take the base minus 1, 8 minus 1 is 7. That means I have 7 symbols in this octal number system. And so we use the digits 0, 1, 2, 3, 4, 5, 6, 7. We use the digits 0 through 7. The digit 8 and 9 are not allowed. So when we get to 8 or 9, what we do is just like in base 10, When we get past 9, we count 1, 2, 3, 4, 5, 6, 7, 8, 9. We start to repeat digits. For 10, we say 1, 0. For 11, we say 1, 1. For 12, we say 1, 2. We do exactly the same thing in octal and all other number systems. Once we run out of digits, we start to repeat digits. And I'll show you that in just a second. So here is a comparison of octal and binary. You can kind of get an idea looking at this slide. Even though the data inside the digital device is actually held there in binary, you can see why you might want to represent it in octal, because it takes one octal digit can represent 3 binary digits. So if I have any binary number, if I write it in octal, I only have one number to remember. It might be easier to remember a 6 base 8 than it is to remember a 1, 1, 0. So again, both the number systems we'll look at today, octal and hex, are for convenience of humans. Anything that goes into a digital device gets converted to binary, it gets converted to zeros and ones. But we can play that same game that we played in the last time with binary, where we did that position weighting. Remember what we said was that if we have any number system, if I start counting the places if I go from left, if I start counting and I number each space, start counting at 0 and I number each space. This is the 0 position. This is the first position. This is the second position. If I start counting with 0 here, then all I got to do is write that base to the position power. So this will be the 0 position. So I write this as 8 to the 0. This is the first position. This will be 8 to the first, and so forth. And by doing it that way, you can get the weights or the place value of any number system. So in the base 8 number system, this first place right here, 8, let me see if I got my pencil. This first place right here, 8 to the 0, well, that's 1. 8 to the first, that's just an 8. 8 to the second, that's just a 64. And so we can get the place value of any number system, even one that we make up. And just like in base 10, the symbol here tells us how many of these things we have. So I got 4 64s, 4 times 64. I got 6 8s, so down here I got 6 times 8. And I got 2 1s, so down here I got 2 times 1. 4 by 64, 256. 6 by 8, 48. 2 by 1 is 2. If I add those up, then I get this number. So a 462 base 8 in our number system is a 306. So this right here is exactly what we did when I showed you base 10 with place value. It's exactly what we did when we showed you base 2 in binary. And every number system is all done the same way. And once you see the pattern of what you're doing, it's actually pretty easy. So given this place value or position weighting or whatever you want to call it, you should be able to take a number, an octal number, and convert it to decimal. So this slide, you want to mark it, shows you how to convert octal to decimal. And I might ask you to do that at some point. Now, what about going the other way, octal to binary? That's important because this is what the actual machine is doing. If you have a device where you can enter base 8 number into the device, then it has to convert it to binary. What you do, if you want to convert a base 8 number, and I didn't put the 8 here. There's a little 8 right here. This should be a base 8. So it should be an 8 subscript right there. But this is 462 base 8, so that's an octal number. And what I want to do, if I convert it to binary, is really, really easy. All you got to do is take each number here and represent it using 3 bits. So a 4 in binary, if you remember that 8421 code, a 4 in binary is a 1 0 0. So I represent this number right here using 3 bits. I represent this number right here using 3 bits. And I represent this number right here using 3 bits. I just push the numbers together and I got a long binary string, but I've converted this base 8 number to base 2. So a 4 in binary is a 1, 0, 0. A 6 in binary is a 1, 1, 0. And the 2 in binary is a 0, 1, 0. So I put all these bits together, and that long string of bits represents this number right here in binary. But this slide shows exactly why you don't want to try to remember a group of zeros and ones. It's common in digital devices to have the actual machine language, the zeros and ones, but when you write it down, you write it in another number system because it's much easier to remember. It's way easier to remember 462 base 8 than it is to remember 1, 0, 0, 1, 1, 0, 0, 1, 0. So this kind of helps you appreciate why we might want to write a number in octal. Octal. So I want to jump now to hexadecimal. Hexadecimal is base 16. So we go from base 8. Base 8 we said was kind of a natural fit, a natural number system to use with digital devices because 8 bits is a byte, so the number 8 is just kind of good to use that. But what about base 16? Why would we want to use base 16? Well, remember when we talked about word size, we said that if I have 4 bits, that's a byte. If I have, I'm sorry, I said that wrong. If we have 4 bits, that's a nibble. If we have 8 bits, which is usually what we deal with, we usually deal with 8 bits. If we have 8 bits, that's a byte. 8 bits is a byte. But when we get to the word, we said a word is machine dependent. And what I mean by that is, let's say you're going to build a computer. If you're designing a computer, you can make your word size any size you want. In theory, you can make it any size you want. I know a couple days ago after class, one student asked about the Windows operating system. They mentioned it was a 64-bit system, and they asked, well, is this what we mean by word size? Yeah, what happens is the bigger the word, when you move information around, you can move it around in word sizes of 64 bits, 32 bits. You can make the word as big as you want. So you might think to yourself, well, hell, if that's the case, let's just have a unanimous, increasingly, amazingly large word. Well, the problem is the bigger the word size, the more complicated your circuitry. Because remember, it takes this and or not logic and variations of it to move around and to process this data. So anytime you have a big word size, there's always a trade-off. Having a large word size enables you to move information faster because you have a bigger chunk of information. If you have in theory, let's say you have a 32-bit word and another machine has a 64-bit word. If I reach in and grab 64 bits, I'm going to move a lot more information than if I grab 32 bits. So, but the trade-off is the circuitry is going to be a lot more complicated. Speed will be faster, but the circuitry is going to be more complicated. So, always a trade-off in engineering, as I'm sure you know. But anyway, back to this slide. Look at this slide. This slide compares decimal, which we understand, to binary, which computers understand, to hex, which we want to understand. So let's look at how this works. So in decimal, what happens, we start counting with 0, and we get up to 9. So once we get to 9, then we got to start repeating digits. We start repeating these. Once we get to 9, we start repeating these. And so I start repeating this. Right here, I start counting over 1, 0, 1, 1, and so forth. Well, look at what happens over here in hex. In hex, we want one symbol to represent each of these digits, 0 through 15, because we have 16 places you want to represent. 16 is natural because many machines have a word size of 16 bits. As a matter of fact, the simulation software that you're going to use for this class, the input-output modules have 16 connection points. You can connect to one module 16 sensors or switches or buttons. You can connect 16, their numbers 0 through 15. And so the word size that represents that input module, there's a place for every bit. If there's 16 screw terminals, then you need a word size of 16 bits to operate that input module or output module. And so many devices or PLCs have 16-bit words. And so because of that, this hexadecimal system is kind of a natural. Now notice here though with hex, hex and decimal are exactly alike. From 0 through 9, they're exactly alike. It's 0 through 9 here, and then over here is 0 through 9. They're exactly alike. Where it differs is once you get beyond 9, then look at what happens. Here I start to, over on the decimal side, I start to repeat 1, 0, 1, 1, 1, 2, 1, 3, all the way down to 15. But what I do with hexadecimal, what I do is I use letters of the alphabet to replace the 10. I use an A. I use a B to replace 11. I use a C to replace 12. All the way up through 15, I use an F to represent 15. So if you see a funny looking number where you have like letters and numbers mixed up in the digital system, then what you're looking at is hexadecimal. So what you want to remember, this actually is quite easy. It's easy because it's the same as decimal from 0 through 9, and all you got to remember here really is that A has a value of 10. The letter A in hex has a decimal value of 10. The letter B in hex has a decimal value of 11. The letter C, 12, all the way up to 15. And so if you remember that, like remember that B right there, that B represents an 11. If you remember A through F is 10 through 15, then this number system is a piece of cake. So let's apply that to what we looked at when we looked at binary, and when we looked at base 10, and when we looked at octal just a few seconds ago. Remember what I do is I start counting these positions, 0, 1, 2. If I do it that way, then the base to the power of the position becomes the place value. So this 16 to the 0 has a place value of 1. The 16 to the first power means the place value here is 16. And 16 to the second power has a place value of 256. And I can keep going over here to the left if I wanted to. So let's say I have this number. Now again, I don't have this subscripted, but what this number really is, I'm talking about this number. What that number really is a 1B7, and there should be a little 16 over here subscripted. I don't know why I don't have that. This is a 1B7 base 16. If I wanted to convert that to decimal, I had to use this right here to get the place value, which I have down here. I got the 256, I got the 16, I got the 1, and then this tells you, this right here, that number tells you how many of these we have. So I got 1, 256, I got B of these things, but remember B is an 11 from that table before. And I got 7 of these. So I got 1, right here I got 1 by 256. I got B is an 11, so I got 11 by 16. And I got a 7 by 1. So when I do my math, I get 256, 176, and 7. I add those up. And what I figure out is that a 1B7 base 16 in our number system is 439. And so again, with this, you want to be able to convert a number from base 16 to decimal, so we can see what we're dealing with. So somebody asked me, or they messaged me in the last class, and we were doing some binary arithmetic, and they said, wouldn't it be easier to convert to base 10, do the arithmetic, and then convert back? And the answer is, well, yeah, it would be easier, but then you don't learn anything. The purpose of that arithmetic discussion last class was so you can see what the processor is doing. You can understand it. Not that you have to actually go out and do binary arithmetic, but you can at least understand kind of what the processor is doing with those zeros and ones. Well, here is a good case where if I wanted to add numbers in base 8, or if I wanted to add numbers in base 16, then I would do exactly that. I would convert it to base 10, I would add them and convert it back to base 8 or base 16. So you can actually do math with base 8, or you can do math with base 16. And when you do it, I think it's easier at that point to convert it to base 10, do the math, and then convert it back to the whatever base you're in. So now the real power of this is not so much going from base 16 to a decimal. The real power is how many bits, what word size can you represent using base 16. So this next slide shows you the big advantage of using hex. Look at this. So if I want to convert hex to binary is really simple. All I do is I take each hex digit and I write its binary equivalent, but I got to use 4 bits. Now remember, when we talked about octal just a few minutes ago, when we want to go from octal to binary, we represent each octal digit using 3 bits. Here, if I want to go from hex to binary, I'm going to represent each hex digit using 4 binary bits. So what I do is I write a 1. I show 0, 0, 0, 1 in binary. This B, now remember, B is 11. From that chart, B is 11. So right here, I have an 8, I have a 2, I have a 1. If you remember that 8421 code I showed you, this first one's an 8, this is a 2, that's 10, and that's a 1, so there's 11. And then 7 is, of course, a 1, 1, 1. Got a 4, 2, and a 1. I put all those bits together, and I got this long, huge number. Now look at that. Would you want to remember 1B7 base 8? Or would you want to try to remember 0, 0, 0, 1, 0, 1, 1, 1, 0? It's much easier to think about or to talk about that number in hex than it is to actually use the binary digit. So hopefully this points out why it's way more convenient to represent binary information using other number systems than it is to do actual manipulation of binary bits. Hexadecimal, octal are used in common, and the PLC simulator, which you're going to use, is based on octal. Actually, it's based on hexadecimal, I'm sorry, because you have 16 terminals, screw terminals you can connect to. So it's a hexadecimal oriented machine. All right, so anybody have any questions over that first slide? We got 2 slides and a chart to look at. I want to move to the next PowerPoint, but I first want to see, anybody want to ask me any questions over that first PowerPoint? Okay, let me get to the next PowerPoint. So the next PowerPoint deals with codes. Codes. Now, here's what you want to remember about binary numbers and binary codes. The difference between the two. A binary number always uses position weighting. What I mean is a binary number always uses place value. A binary code doesn't necessarily have to use place value. Most often, binary codes will use the sequence of bits to represent a piece of data. So if I have 2 pieces of data, I can code it by just manipulating the bits. If I have a different series of bits, I can represent different pieces of information. So in general, binary numbers have always have place value. In general, binary codes, the bit sequence is what we use to represent different pieces of data. However, there are certain binary codes that do use position weighting. So I don't want to say, strictly speaking, you can't have binary codes where they have a type of a place value. So here's some common codes here listed that you can talk about when you talk about digital devices. So BCD stands for binary coded decimal. That's important. Binary coded decimal. There's gray code. That's important. And then there's ASCII. So BCD, binary coded decimal, we'll start talking about that. That's important because when you want to use a digital display, when we use digital displays or digital readouts, then that's a case where you would use BCD, binary coded decimal, because then you're able to light up or control each digit of a digital display. Gray code is what we call our error minimizing code. So if you want to move information back and forth, sometimes bits can change or they can be lost. So gray code helps us to minimize the chances of a bit being changed when you transfer information from one place to another. So I'll talk about that. And ASCII is really important because when you type anything on any kind of keyboard, that character is represented in ASCII. And I'll show you an example of that. And then we'll briefly talk about encoding and parity. We won't talk about, I think one of your homeworks deals with parity, so I'll let you kind of learn about that by doing the homework. So let's get into the slide. And the first one we want to talk about, the first code is BCD. So again, BCD stands for binary coded decimal. And let me just show you something real quick. So you know the digital display, the digital readouts that you have, like on an alarm clock or anytime you're using some kind of readout or maybe a thumb wheel that you can change the numbers, you're using something like that, you have these digits. So what happens is you have a LED. And you probably know a LED is a light emitting diode. So it's a light. And you have this light it's called a 7-segment display. It's like an elongated LED. So usually LEDs are round, but for the 7-segment display, they'll have a long, little thin LED like that. And so the numbers, it looks like this. You have an LED like this, LED like that, like that, like that, like that, like that, and like that. So you might have a couple of these LEDs. And then what happens is each LED is called a segment, and you can address each segment and light it up to make the symbols 0 through 9. So let's say I want to make a number 9. I can light up this segment. I can light up this segment, this one, that one, this one, that one, and that's the number 9. Or maybe I want to make the number 7. I light up this segment, and this segment, that's the number 7. If I light them all up, then that looks like an 8. So when you have any kind of situation where you're trying to have individual digits that you display, that's the case for BCD. So I'll show you that. And there's an exercise we do, I think in one of your design problems you'll do for me later on. And I'll show it to you where this comes up again, so I'll probably end up talking about it again. So, BCD provides a means of converting easily from decimal to binary. This is the big one though right here, the one I was trying to explain. These LEDs are use BCD when you want to use these 7-segment displays, and they're used quite often. Any kind of digital readout, even on your cell phone, there's a digital readout. When you type a number, it displays, that's a digital readout. And that would be a case where you could use this code we're talking about, BCD. So what you want to remember is these two last points right here. Remember these, that number 1. BCD uses 4 bits to represent each digit. 4 bits to represent each digit, 0 through 9. And I'll show you what I mean by that in a second, but mark this slide, the last 2 bullet points. BCD uses 4 bits to represent each decimal digit. And then the largest decimal digit that can be represented by 4 bits is a 9. A 9 is the largest number we can represent, not by 4 bits, but by BCD. So you can't go beyond 9. And it's easier for me to show you this chart than trying to explain it. So here's what I'm trying to tell you. Look at this chart. Okay, so right here we have binary, we have BCD, but then we have decimal. So compare the decimal column to the BCD column. So if I want to represent the decimal number 0, then I use 4 BCD bits, 4 zeros. If I want to represent the decimal number 1, I got to have 4 zeros and a 1. It's very important that you students have a tendency to drop the zeros because you say, that's all right, I have a leading 0, it's not worth anything. You cannot do that in digital systems because these numbers have to be held somewhere, and they're held in something called registers. We talked about shift registers the first week of class. So if you have a 4-bit register, you cannot just say you had this number right here. If you have a 4-bit register, then what you have is you have this, think of a register as just a box, and it has these spaces in it, like this. And then you put the bits in here. You can't just put a 1 right here and not have anything in these other 3. You got to have something there. And that's something in the digital device is going to be a 1 or a 0. It can't hold nothing. It can only hold a 1 or a 0. So because registers have a certain fixed size, you always have to put these leading zeros in here. So you always represent, I don't care if you have a 0 or a 0 out front, you always represent each decimal digit using 4 BCD digits. So 0 would be 4 BCD zeros. A 1 would be 0, 0, 0, 1. A 2, then we did, over here we're just counting in binary. Basically from 0 to 9. This 9, this right here on the 8421 code, that's an 8. And that's a 1. If I add those together, I get 9. So a 9 in BCD is a 1, 0, 0, 1. So BCD, it's just like binary over here. They're the same. Each of these numbers are the same. 9, 9, 8, 8, 7, 7, and so forth, all the same. But where it differs is once you get beyond 9. So what we said earlier is, once I go beyond 9, then in decimal, I need 2 digits to represent. I start counting 1, 0, 1, 1, 1, 2, 1, 3, for 10, 11, 12, 13, and so forth. Well, to represent that in BCD, you need to represent like this number using 4 bits. So that's what this is right here. That's the, actually, that's not right. Let me see if I can erase that. Still trying to learn. There we go. All right. So what I was trying to show you is the 2. So this 2 for number 12, I got to represent that 2 using 4 bits. So this 2 right here is represented right here. And then this 1 right here is represented right here. So I use 4 bits, 4 binary digits to represent each digit. And that allows us to use circuitry and devices to run this to a 7-segment display or some kind of device where I want to either enter decimal digits or read out decimal digits. I do so in BCD. Well, you might think to yourself, well, how do I differentiate a BCD number from a binary number? Here's how you would do that. You got this decimal number, 7,863, and you want to represent it in BCD. So the way you do that is each one of these symbols right here I have to represent using 4 bits. So here's the 4 bits that represents the 7. Here's the 4 bits that represents the 8, and the 4 bits that represents the 6, and then the 3, and so forth. And what you would do is you would subscript that. Normally we would subscript base 2, but here we just write the actual letters BCD. So I can distinguish just between a regular binary number and the BCD number. Now what happens is when you do it this way, you can run this whole number into circuitry that can convert this to BCD or this to decimal. And I can use a encoder or decoder to display or either enter these decimal digits. And again, you'll see that later on. Here's a kind of an overview of a whole system that uses BCD. So here's a good example. So like right here, let's say this is some kind of device where you can put in regular decimal numbers. Maybe these are like a combination. There's something called a thumb wheel, like a combination lock. You can spin these, and maybe you got 6, 4, 1, 9, and you want to enter that into the PLC input module. Well, this thing right here would have to enter this, would go into the input module as BCD, binary coded decimal. And then inside the PLC, this whole picture right here, this is all virtual stuff. This is what's happening inside the PLC. So this input module is going to enter that number as BCD, but even though BCD is a series of zeros and ones, you still got to have circuitry to convert it from BCD to regular binary. And I'm doing air quotes, but you can't see it. Because BCD is not machine language. Regular binary is machine language. So once we get to binary, then we can process it. By process it, I mean whatever you're doing to those zeros and ones. And then maybe you got some kind of output you want to display. So over here we have a digital readout. And again, if I have a digital readout, I got to display each one of these symbols right here, like the 1, the 7. I got to use BCD to display those. So the bottom line is, anytime you have any kind of digital display or anything that acts like a digital display, where you're displaying or entering individual decimal numbers, then you would use BCD. I think really you want to remember BCD stands for binary coded decimal, and then the project that you'll have that involves this, you remember that this is not regular binary. Next code is called gray code. And I'm not going to read this slide to you. Just point out a couple things. The second bullet point, gray code does not use position weighting. So where BCD, there's position weighting, because really all you're doing with BCD is writing in binary for each, using 4 binary bits for each decimal digit. So you're actually kind of using position weighting there. But here, with gray code, you're not using position weighting. That's one thing. And let me show you what this looks like, and you'll see why this is important. So if you look at the column that says binary, and you look at gray code, and then you read the box I have right here, that's what's important. So right here it says only 1 digit changes as you move from one number to the next in gray code. So for example, let's look at binary. If I start counting 000, 001, when I start counting, as I move from one binary number to the next, well, this one only 1 bit flipped. This one, 2 bits flipped, like that one flipped and that one flipped. Look down here though, right here, look at these two. When I go from a 111, which is a 7, to a 1000, which is an 8, all the bits change. You might think to yourself, well, what's the big deal with that? Well, anytime there's a change of a bit, when it goes from a 0 to a 1, or from a 1 to a 0, remember, we're moving, these bits are not static. They're actually moving around as digital pulses. When you connect to a web page, if the web server is in California and you're in Cincinnati, when you render that web page on your computer or cell phone, you're actually moving zeros and ones back and forth over a network 4,000 miles away if that web server is in California. You got to move all those zeros and ones to represent all the data on that web page. Every pixel, every sound, every video has to be transferred and then rebuilt on your screen. So the chances that you can lose a bit or a bit could flip, it's a big chance that could happen. And then there's some kind of noise or static or when I say noise, I mean electrical noise. There's always a chance that you can cause the bits to flip or change when you don't want them to change. So this code is called error minimizing code, because when you code or encode using gray code, then you only change 1 bit at a time, and sometimes that could help you to have less errors. So this next slide, I want to mark this one because we're going to use gray code in here, but you don't have to memorize. I'm going to point out we're going to use gray code as a technique here later on to help us minimize complicated logical circuits. So I'll point it out. Again, I'll say, hey, we're using gray code. So you'll remember what it is, but I'm not going to test you over gray code specifically. The only thing you got to remember about gray code is what's on this slide. I'll probably ask, like, what's the advantages of gray code? Well, here you go. Gray code is considered to be error minimizing code. And the reason is because only 1 bit changes at a time as you move from one number to another. So for gray code, just mark this slide, study this slide. As far as the way the numbers are, don't worry about it. You won't have to memorize it or anything like that. We'll use that in something called a K-map. And when we get to K-maps, I'll point out again to you that we're using gray code. Now, there's one more code. We talked about BCD, binary coded decimal. We talked about gray code. Gray code is an error minimizing code. There's one more I want to talk about, and it's called ASCII code. You may have heard of ASCII. If you're in the computer science, you probably heard of ASCII code. So ASCII stands for American Standard Code for Information Interchange. American Standard Code. So here's what happens. Anything you type on the keyboard, if it goes into a computer, it's got to be represented as zeros and ones. So what I'm saying is, let's say you have a computer or your cell phone and you type the letter A. The letter A is represented as zeros and ones. Let's say you type the letter B. Well, remember there's two B's. There's an uppercase B and there's a lowercase b. So for every character on the keyboard, you have to have a code to represent each character, a binary code to represent each character. So there's a binary code to represent uppercase A. There's a binary code to represent the lowercase a. There's a binary code to represent uppercase B. There's a binary code to represent lowercase b. As a matter of fact, there's a binary code for every symbol on the keyboard. So what I'm saying is, they're just not alpha, like A, B, C, D, upper, lowercase. You also have the comma. You also have the exclamation point, the star, the pound. Every single symbol on your keyboard has to be represented in zeros and ones. And so we use this to do that, ASCII. Now, the easiest way is for me just to show you this. So let me show you what this ASCII looks like. I have a table that I can show you. So here is ASCII code. And if you look at this, since we studied binary, octal, and hex, now you know about that. What you have here is, now remember on your keyboard, and I said every symbol on your keyboard, but there's certain things like you ever get to stick up, maybe you hit a key and you hear a bell ring. You hear a bell ring on your computer, or maybe even the sounds have an ASCII code. Everything that you do on that keyboard or can do, if you can press a key and make a sound, then that sound has an ASCII code. So this table that you see right here is the ASCII value. Oh, wait a minute. Let me get my pen. Right here, this column right here is showing the symbol, and here's the binary representation for whatever it is we're talking about. So what I'm saying is, let's go over here. Here is the letter A on the keyboard. Now that's the uppercase A. Over here is the lowercase a on your keyboard. Well, how's that A represented? On the keyboard, it's represented like this, in binary. If you type the letter A in a Word document, what goes into the processor is what I'm circling right now. If you type a lowercase a, what goes into the processor is this. There's a set of binary digits that represent each and every character on the keyboard. So even the @ sign, look at this. Here's the @ sign. Well, here's the binary code for the @ sign. If you go down here, you'll see some really weird, like right here on your keyboard, there's a delete key. Even though you're not typing anything when you hit the delete key, there's got to be some kind of binary code for delete. Well, here it is right here. This is the binary code for delete. So it's actually possible, if you know what you're doing, if you're a hacker, a computer hacker, and you have this ASCII table, you can actually operate somebody's keyboard, if you know how to access it through the network, by sending it the ASCII information. You can have something deleted without actually hitting the delete key if you know the code for delete. And that's kind of what ASCII does. Now, you might want to know, well, what are all these other things? Well, all they do here is like, let's use the uppercase A. So the uppercase A, here is the binary code for uppercase A right here. I got a circle. But they also display this code, this binary code. They display this in decimal. So if you convert this code to decimal, you get the number 65. If you convert this code to octal, you'll get 101 base 8. If you convert it to hex, you get 41 base 16. So this table is showing you the code, the binary code in decimal, octal, hex, and you can see it's much easier to remember that an A is decimal number 65 than it is to try to remember the sequence of bits. So ASCII code is actually pretty interesting. I wish we could have more time to talk about it, but again, I'm not going to ask any specifics about this. Just kind of know that ASCII code is represented It's used to represent anything on the keyboard. Now you might think to yourself, well, okay, Singleton, hold on. What about other languages? What about, was it Mandarin Chinese? And you got all these other countries, because it said American code for information interchange. American code. Well, that's because the computer was, I won't say discovered or produced here, but the United States was a big driving force back in the 60s and 70s for computer science. And so, a lot of this is based on American technology. But now we have other languages. We got to represent, not everybody speaks English, so we got to have a code to represent any language. And I forget the name of that code. I can't remember the name of it right now. But the thing is there's the ASCII code. I want you to know about that. Just know what the letters mean. But there's another one. I think it's called Unicode or something like that. I can't remember what it is. But there's another code, kind of like ASCII, and it's supposed to encompass all the languages, all the major languages known that might use some kind of electronic device as a keyboard or on a keyboard. One more thing, guys. I'm running out of time, but let me go back to my PowerPoint. And I was on slide right. Where was I? Right here. We were talking about ASCII. So this is the next slide. I'm not going to say anything about that slide. Let me move to this one. The only other thing that was on the title of this PowerPoint was this idea of a parity bit. I'm not going to say anything about parity bits other than to say that parity bits are used for error checking. Error checking. When you send information over a digital system, how do you know that what you sent is what the other digital device received? One way to do that is by using parity or parity bits. So the reason I'm not going to go into it is because this is an assignment that's assigned to you, and part of the assignment is you researching parity. So I'm not going to say anything about that, and that kind of ends our presentation for today. So anybody have any questions? I see I still got 28 people hanging around, so that's good. Anybody have any questions for me before we start our weekend? Any questions or comments, concerns, thoughts, ideas, anything you want to say? I don't know if you guys know it, but I take care of my mom's almost 80 years old, and since I'm the only one that's single, my brothers and sisters and all that, I take care of her, and she goes to get her COVID shot. I'm so happy because I've been so stressed out because we have all these grandkids that come back and forth, and I'm doing my best to try to ward them off and keep them away. But she was having, I don't know, she was kind of chickening out. She didn't want to get the shot. I can't wait to get my shot. I just can't wait. But she was kind of afraid. So I went to feed my dogs in my apartment, and when I came back, I saw her wheelchair outside. And she had went to get her first of 2 shots she has to get. So I'm kind of happy because that's been stressing me out. But anyway, I can't wait to get my shot. And you guys, you're young. You don't have to worry about it as much as we do. But you guys, please stay safe. And I think the quiz is posted. I posted it early because another student needed to do something that worked out better for them if we posted it early. I also put up the link for the simulation software, which you got plenty of time. You don't need it right now. And then over the weekend, somebody asked about putting up a picture of the book, the cover of the book. I'll do that either today or tomorrow over the weekend. And I think your homework, everything's on Canvas. So any questions or comments, guys, just text me. Please stay safe. Have a great weekend, and I will see you on Monday.